Tēnā koto, tēnā koto katoa. Today we are looking at specific heat capacity as part of the Energy External Standard for Level 1 NCEA Physics and Earth Space Science. So, caution, always blow on the pie. So think about this. You've bitten into a meat pie and you've scalded the top of your mouth. So the outside is warm to touch, the pastry, but the inside is basically thermonuclear. It's been in that pie warmer since 2 a.m. It's very hot. But the pie itself has been cooked together, the pastry and the filling. So why is the centre hot and the outside pastry kind of warm to touch? It's because the filling has water in it, which means it has a higher heat capacity than the pastry. So what is this heat capacity? Well, it's basically a measure of how much energy a material can store. And it is the energy essentially needed to raise the temperature of a kilogram of that substance by a degree Celsius, and the units are joules per kilogram degrees Celsius. So here's 3 materials: copper wire, a limestone slab, and water, so a kilogram of them. And they're basically heated at the same temperature for 10 minutes. Which one do you think will get hottest? So pause the video now and have a little think. Okay, so welcome back. So looking at the copper, limestone and water. So the copper wire, if it's heated for 10 minutes, is at 82 degrees Celsius. The limestone is at 65 degrees Celsius and the water is at 43 degrees Celsius. So the copper, we say, would be became hot because it has the lowest specific heat capacity. It doesn't require much energy to increase its temperature by a degree Celsius. Whereas the water requires a lot more energy to increase its temperature by a degree Celsius. Okay, so what the water's done is it's absorbed the energy, the heat energy from the surroundings without actually having its temperature, the average kinetic energy of its particles, increasing. So they're not moving around as much as those in the copper. We also have here some numbers of specific heat capacities of different materials and some questions. So which will get hottest, a kilogram of glass or a kilogram of iron? Which material is used in heat radiators and why? And what other materials could be used in heaters? And which feels colder for an hour in the fridge, limestone or copper? Okay, so again, pausing the video and then coming back when you think you have the answers, and we'll go through them. Okay, so welcome back. So the first question is which will get hottest, 1 kilogram of glass or 1 kilogram of iron? So if we look at the specific heat capacities, iron is at 460 joules per kilogram degrees Celsius, whereas glass is at 840, roughly double. Okay, so because iron has a low specific heat capacity, it requires less energy or less thermal energy to warm up degrees Celsius. So the answer would be iron, would be the hotter of those two. Okay, makes sense because that's why we make glass windows. Windows out of glass. So which materials are used in heat radiators? So primarily water is used in heat to heat radiators. Why? Because it requires a lot of energy to heat it up. True, but also it requires a lot of time for that water to release that heat energy back into the surroundings. So it's kind of a two-way street. That would also mean that another material that could be used is oil. Again, has a very high specific heat capacity, so it takes a lot of time to release that heat energy over time. And which will feel colder after an hour in the fridge, the limestone or the copper. So when you think about it, a aluminium can in the fridge, really cold to touch, compared to say a limestone rock. So the answer is copper. Okay, so even though it takes a lot of heat energy to, not much actually, not much heat energy to increase it by degrees Celsius, it also is very willing to release that heat energy very quickly. So in terms of calculating specific heat capacity, it's basically using the equation here, E thermal equals M times C times delta T, where M is mass in kilograms, C is the specific heat capacity we've just been discussing, and delta T has no units, because it's just a change in, but the temperature is always measured in degrees Celsius. And of course, E thermal is measured in joules because it's a form of energy. And in terms of the equations that you need to rearrange, those are how you rearrange them. So if you want to work out the mass, it's going to be the E thermal divided by the change in temperature times specific heat capacity. Change in temperature will be E thermal divided by the change in, or the specific heat capacity times the mass, and the specific heat capacity is going to be E thermal divided by the mass times the change in temperature. And that's pretty much all you need to know about specific heat capacity.